Hello and welcome. This is a video about integrals involving exponential functions. So exponential functions show up in the growth of populations, also radioactive decay, all things like biology, chemistry, physics. They show up in a lot of different applications. We're going to be focusing on the math and the calculus part of it. So recall that d dx, the derivative of e to the x, is actually just e to the x, which is why e to the x is such an important function, because it's one of the very few functions whose derivative is itself. And if you remember, derivatives and integrals are inverse operations, which means if you start on the right side and work to the left side, that should give you an integral. In other words, since the derivative of e to the x equals e to the x, many of you probably already know that the integral of e to the x dx is equal to e to the x. But of course, if it's an indefinite integral, you have to write plus c at the end, which represents a constant, the constant of integration. So e to the x is actually the easiest function out there to take the derivative of and also to take the integral of. But remember, you won't necessarily have x be the inside of your integral. But even so, if you have the integral of e to the u, and then you write it as a form where it's in the form du, so the integral of e to the u du, that's still going to be e to the u plus c. All right, and remember, if you're taking the derivative of e to the u, where u is a function of x, then it's still going to be e to the u, but you would have to use the chain rule. So it would be e to the u times u prime. Okay? But you can watch my previous lesson on derivatives of exponential functions. In this lesson, we're going to be focusing on the integrals. And while it's an easy formula to start with, it's very helpful. Some integrals can be made a lot more straightforward if you write them as an exponential function. Okay, so let's see some examples. Okay. Example. Evaluate each integral. Evaluate each integral. So let's start with a relatively easy one. Okay, problem number 1 is going to be the integral of parentheses e to the 5x plus 7e to the negative x dx. Okay, so the integral of e to the 5x plus 7e to the negative x dx. So using this new rule that we're learning here, the integral of e to the u du equals e to the u plus c. Of course, to use u substitution, you can't have dx, you actually have to have du. So let's figure out what we need to do here. So for these integrals, remember you can split them up into multiple terms. So in other words, I can distribute the integral symbol to each of those terms. So that's going to be the integral of e to the 5x dx plus, well, 7 is a constant, so I can bring it out front of the second integral. So it's going to be plus 7 times the integral of e to the negative x dx. Okay, and you don't have to write the step I just did, but I'm doing it on this first one, just in case you don't remember your calculus 1. Okay, and then what we have to do for each of these is we have to write them in the form integral of e to the u du. In other words, we have to use u substitution, and when you're doing u substitution, you generally want to choose u to be the inside of your composite function. So for this first integral, the inside of our composite function is 5x, right? So u is going to equal 5x. So for the first one, we let u equal 5x, okay? And then du is going to equal 5dx, or if you think of it this way, du dx equals 5. All right, and then if you want to do it the way I teach it, I usually isolate dx. So I multiply both sides by dx and divide both sides by 5. So I get du over 5 equals dx. Now this u is only going to work for our first integral. But right now we're just, focusing on the first integral. So for this first integral, this is our u. So we've got the integral of e to the u times, well, we can go ahead and plug in du over 5 for dx. Okay, so our first integral now is going to be the integral of e to the u times du over 5. Integral of e to the u times du over 5. And of course, the integral of e to the u du is just going to be e to the u. And because this one is actually an indefinite integral, our answer is going to have a plus c at the end. But for now, we can just bring the 1/5 out front. So we have 1/5 times the integral of e to the u du, which is just going to be e to the u. So we have 1/5 times e to the u. But our first u that we work with here for this first integral right here is 5x. So instead of writing e to the u at the end, I'm going to write e to the 5x. So we have 1/5 e to the 5x, and we've finished the first term, the first integral. And remember, we're going to need a plus c over here at the end, so I'll go ahead and write it just so we don't forget. Okay, so now we're going to take on this second integral. So for the second integral, I already factored out the 7. So once again, we have to do u substitution, and we let u be the inner function. So here the outer function is e, and the inner function is negative x. So for the second one, let me use a different color for this one. For this one, we're going to let u, this is going to be a different u, so I'll do it in a different color. For this one, we let u equal negative x. And then taking the derivative for our u substitution, we're going to get du dx equals negative 1. And then if we isolate dx, we're going to multiply both sides by dx and divide both sides by negative 1. So we're going to get negative du equals dx. Okay? And then we can go ahead and plug in. We can go ahead and plug in here. So I'm going to go ahead and plug in negative du in place for dx. Okay? And remember, negative x is actually our u for the second integral. Okay, so plugging in, we still have a 7 out front. So we're actually going to have 7 times the integral of e to the u times negative du. Because remember, dx is actually negative du here. Okay, so that's what we're plugging in there. Okay, and then after that, we can go ahead and factor the minus out front. And then once again, we're going to have, inside of the integral, we're just going to have e to the u du. And the integral of e to the u is just e to the u. Okay, so we're going to have minus 7 times e to the u. But remember, this u is actually a different u than the first one. This is the u for the second integral. So for this one, when we plug it back in, it needs to be u equals negative x. Okay, so instead of negative 7 e to the u, we're going to have negative 7 e to the negative x. Okay, and that gets us to our answer. So our answer, since we already did the first integral, we're going to go ahead and combine all these. So we have 1/5 e to the 5x minus 7 e to the negative x plus c. And so hopefully that's not too bad. That was supposed to be a relatively easy one. That's similar to your first homework problem. Okay, and remember, when you don't have numbers to plug in or limits of integration, that's how you know that this one was an indefinite integral. And because it's indefinite, you don't plug in numbers at the end, you just go ahead and write plus c. Okay, so let's take a look at example number 2. This one is the integral from ln of 5, so natural log of 5, to natural log of 9. So the integral from ln of 5 to ln of 9. And here we're doing a very easy integral. This one is actually just e to the x dx. Okay? But what's different about this one is actually a definite integral. So notice when you have a number on the top and the bottom, those are called your limits of integration. And this one is a definite integral. And with definite integrals, instead of writing plus c like we did on the last one, well, the last one was an indefinite integral, so we wrote plus c. But because this one is a definite integral, we're going to be plugging in the numbers at the end. Okay, so plug in limits of integration is what they're called. Limits of integration at the end. And remember, it's the fundamental theorem of calculus part 2, which is you plug in the top number into the function, and then you subtract the entire function evaluated at the bottom number. Okay, but this one is so easy that, remember, the integral of e to the x dx is actually just e to the x. Okay, so the integral part is ridiculously easy here. So that's just e to the x. We don't even have to do u substitution with this one. However, we do have our limits of integration. And remember, those limits of integration are in terms of the original variable. So that's going to be going from x equals ln of 5 to x equals ln of 9. Okay, so we're going to be evaluating e to the x from ln of 5 to ln of 9. And remember, you plug in the top number first, and then you subtract the function evaluated at the bottom number. Okay, so plugging in the top number, we're actually going to get e to the ln of 9, and then we subtract the function evaluated at the bottom number. So that's going to be minus e to the ln of 5. Now, even though this is a super easy problem, one of the reasons I chose it is just in case you don't remember how logarithms and exponentials work. Remember that natural log is actually the same as log base e. Okay, so that's just a little bit of stuff to remember there that you might not remember from pre-calculus. So ln is the same as log base e. Okay? So what that means is e to the ln of 9 and e to the ln of 5, the e and the ln are just going to cancel out. Because if you have a logarithm and an exponential with the same base, and you compose them with one another, so you have one function and the other function, they just cancel out. So this e and this ln and that e and that ln, those just cancel out. So we're just left with 9 minus 5, which is 4. Okay, so our answer is 4. Pretty cool, huh? Okay, so hopefully that one's not too bad. All right, and most of your homework problems, the early ones are pretty similar to these, so I don't think I need to do any more of those. So let's try to get to some of the harder ones. Okay, so, all right, problem number 3. Problem number 3 is going to be the integral of e to the 7 root t over root t dt. Okay, the integral of e to the 7 root t over root t dt. So here, we do have a composite function, and as usual, you want to generally let u, for your u substitution, to be the inside of your composite function. But then the question is, well, we actually have a couple of composite functions here. So we have the e to the 7 root t, that's a function within a function, and then we also have 1 over root t, which is another function within another function. So you might not be sure which one to choose as your u, which is why I'm doing this example. But if you think about it, if we let u be the 7 root t, if you take the derivative of the square root of t, that actually is going to move the square root to the denominator. Okay, so if you do that u substitution, that you're going to have a square root of t in the denominator, and then when you flip it over, that's going to cancel out with this one. Okay, so we actually want to let u be 7 root t here. You could try letting u be root t. That would be okay as well, but it might not work quite as well. It might be a little more complicated, or it might not even be doable at all. But I'm just going to go ahead and choose u to be 7 root t, because I know the derivative of root t is going to move the root t to the bottom, and then it's going to be something that's going to cancel out with this root t on the bottom. Okay, so you'll see what I mean in just a second. So we're going to let u equal 7 root t. Okay, and remember, that's the same as 7 times t to the 1/2, because a square root is the same as 1/2 power. Okay, and then, so that's our u, and then when we take the derivative, we're actually going to get du dt equals 7 times, well, doing the power rule, taking the derivative, we bring the exponent out front, so we're going to have 7 times 1/2, and then we subtract 1 from the exponent. So we're going to get times t to the negative 1/2. Okay, so 7 times 1/2 t to the negative 1/2. And then we can simplify this more. Remember that 7 times 1/2, the 7's actually on the top, so that's going to be the same as 7 halves. Okay, so we're going to have 7 halves, and then for the t to the negative 1/2, I can move that down to the denominator, and that's actually going to become t to the positive 1/2 in the denominator. But remember, t to the positive 1/2 is the same as the square root of t. So we actually just have 7 over 2 root t. Okay, so there's our du dt. And I'm just going to keep doing these the way I like to teach u substitution. So what I'm going to do next here is I'm actually going to isolate dt. Okay, that's how I like to teach it, because it's usually sometimes it takes a little bit longer, but it's nice because stuff cancels out, and my way is kind of mindless, so it's harder to mess it up than the way they do it in the book. So we're going to isolate dt here. So we go ahead and multiply both sides by dt, and then we also multiply both sides by the reciprocal of this fraction here. Okay, so we're going to be multiplying both sides by 2 root t over 7. 2 root t over 7. And of course, we're also going to multiply both sides by dt. So move dt to the right side. Okay, so let me actually go down here then. So that's going to give us, we're going to have 2 root t times du over 7 equals dt. Because everything on the right side, the 2, the 7, and the root t are going to cancel out. So we're just going to have dt on the right side, which is what we wanted. We wanted to isolate dt, if you're following my method for doing these. And then what we can do is we can go ahead and plug in this big complicated thing here in for dt. Okay, so if I go ahead and take this right here and plug it in for dt, then a bunch of stuff is going to cancel out. Okay, so we have 2 root t du over 7. Plugging that in for dt. Okay, so we have the integral of e to the u times 2 root t over 7 du. So 2 root t du over 7. And then we also still have a root t on the bottom, so don't forget about this one. So there's still this root t right here, so that's still right there. But that's good because we want the root t's to cancel out. And they do. So they do cancel out here. So these root t's are going to cancel out. And then we're just going to be left with 2/7 e to the u du. So we can bring the 2/7 out front because it's a fraction and it's a constant. We can just factor it out front. So we're going to get 2 over 7 times the integral of e to the u du. Okay, and of course, the integral of e to the u du is just e to the u. So we have 2 over 7 times e to the u. And then remember, on this problem, this one is an indefinite integral because it doesn't have any limits of integration. So because there's no numbers to plug in at the end, you're going to go ahead and write plus c, which is a constant. And then, of course, you want to, instead of writing u, you want to plug in the original expression in terms of the original variable. So here the original variable was t, and we said that in this problem, we decided that u was going to equal 7 root t. So we need to go ahead and plug in 7 root t in for u. Okay, so we're going to replace this u right here with 7 root t. So we have 2/7 e to the 7 root t plus c. Okay, and that's the whole problem. So that one's a bit more challenging. If you're good with your u substitution, maybe it's not so bad, but it can be challenging because if you miss one little detail, you could get the wrong answer. Okay, cool. All right, so that was our example number 3. Okay, so I'm going to do some more of the more challenging problems now. Some ones that are similar to the harder problems in your homework. Okay, so problem number 4. Problem number 4 is actually an interesting problem because it's the integral of e to the 1 over t, which is kind of unusual, but it's e to the 1 over t all over t squared dt. So this one is another indefinite integral, so at least we don't have to worry about plugging numbers in. So at the end, we're just going to write plus c, because there's no limits of integration. However, here we're going to have to do u substitution, and we are going to have to be careful about what we choose for our u. However, you generally want to let u be the inside of the most complicated composite function you have there. So you've got 1 over t squared. That's not really as complicated as e to the 1 over t. So we're going to focus on letting u be the inside of the composite function e to the 1 over t. Okay, so here we're going to let u equal 1 over t. Once again, the inside of your most complicated composite function is generally what you're going to choose for your u, for u substitution. Okay, so here we're going to let u equal 1 over t. Okay, so let u equal 1 over t. And then we take the derivative of both sides. So we're going to have du dt equals, well, if you don't remember how to do this, remember that 1 over t is the same as 1 over t to the 1. Okay, and if I move that t to the 1 to the numerator, that positive exponent actually changes sign when you move it over the division bar. So that's actually going to be the same as t to the negative 1. Okay, so if u equals t to the negative 1, we can just go ahead and use the power rule, and we can bring the exponent out front and then decrease it by 1. Okay, so we're going to get negative t to the negative 2. Right, because you bring the exponent out front and then you decrease it by 1. So negative 1 minus 1 is negative 2. So du dt should equal negative t to the negative 2. But we can actually move this exponent back down to the bottom again. So if I move this exponent down to the bottom, it's going to become positive again. So we actually get negative 1 over t squared. So we have du dt equals negative 1 over t squared. And then if you do it the way I like to teach it, you don't have to, but the way I like to teach it is now we go ahead and isolate dt. So if we isolate dt here, we're going to multiply both sides by dt, but then we're also going to multiply both sides by the reciprocal of the right side. So we're going to multiply both sides by negative t squared over 1. Okay, so multiply both sides by negative t squared over 1. That's just the reciprocal of the right side. So on the right side, if we go ahead and also multiply both sides by dt, so we move the dt to the right side, we're going to end up with negative t squared du equals dt. And I'm trying to write out all the algebra. You don't have to write out that much algebra. A lot of people can do a lot of these steps in their head. I just want the lecture to be clear. Okay, so now what we can do is we can go ahead and plug in this negative t squared du in for our dt up in the original integral. Okay, so we're going to replace this dt with negative t squared du. Okay, so we're going to have the integral of e to the u over t squared times dt, which we said was negative t squared du. Right? That dt there is just negative t squared du. And then the fun thing about my way is even though it's longer to write out, then stuff should cancel out. So here we can see that the t squareds cancel out. And then we still have a minus left over, so we can factor the minus out front. Okay, so what we've got here is we've actually just got negative of the integral of e to the u du. And of course, once again, the integral of e to the u du is just e to the u. So we're going to have negative e to the u. And then because this was an indefinite integral, we write plus c at the end. But of course, you can't leave your answer in terms of u. U is what's called a dummy variable. So you don't want to keep it at the end. It's just in there temporarily to help you do your math. But at the end, you want to plug in the original expression. So originally we said u equals 1 over t. Right? U is our 1 over t. So we're going to go ahead and plug that in at the end here. So we have negative e to the 1 over t plus c. And I am showing every single step so that hopefully no one gets confused. But when you get more familiar with these kinds of problems, you may find that you're able to do them much more quickly than I'm doing them in lecture, which is good. Because you'll start noticing patterns like the integral of e to the 1 over t squared. Well, it just ended up being e to the 1 over t, which we kind of expected. But then how do we get a minus there? Well, because the derivative of 1 over t has a minus because you have to bring it out front. The derivative of t to the negative 1 brings a minus out front. But really all it gave us was just the same thing, but it had a minus out front. Negative e to the 1 over t plus c. So it's kind of cool to look at the patterns and sort of notice things. But you probably want to just do it the way I'm doing it until you get more comfortable with these kinds of problems. Okay, so that was problem number 4. So let's take a look at problem number 5. Problem number 5. Okay, so this one is a little bit trickier, but it's actually not too bad if you know what to do. So for this one, we have the integral of 4e to the 4t all over 9 plus e to the 4t. 9 plus e to the 4t dt. Okay, so there's a couple of ways you can do this problem. But some ways will not work. So one way you could do it is you could do long division, which would be okay, but it might not be that great. So what you really want to do here is you actually want to do u substitution, but you have to be careful about what you choose as your u. So what I'm going to do is I'm actually going to let u be the inside of the bottom function. Okay, so we have a lot of composite functions here. I know we have a composite function on the top, but we have an even more complicated composite function on the bottom because it's 1 over 9 plus e to the 4t. That is quite complicated. So I think what I'm going to do here is I'm going to let u equal the inside of that complicated composite function. So here u is going to be 9 plus e to the 4t. And of course, if you try u and it doesn't work, then you can pick a different u later, but I'm pretty sure this is going to work. Okay, so I'm going to let u equal 9 plus e to the 4t. Again, that's the inside of the most complicated composite function that I see there. Okay, and then we're going to go ahead and take the derivative of both sides. So we get du dt equals, well, the derivative of 9, because 9 is a constant, is just 0. And then the derivative of e to the 4t is actually going to be e to the 4t times the derivative of 4t. So it's going to be e to the 4t times 4t prime. But what's the derivative of 4t? Well, the derivative of a constant times the variable is just the constant. So that's actually just going to be times 4. Because the derivative of 4t is 4. Okay? And then we want to go ahead and isolate dt, at least if you want to do it the way I like to teach it. So I'm going to divide both sides by 4e to the 4t. Okay, so divide both sides by 4e to the 4t. And I'm going to multiply both sides by dt. So I'm going to move my dt to the right side. So on the right side, all this is going to cancel out, and we're just going to have dt. And then on the left side, we're going to have du over 4e to the 4t. All right, and then we're going to go ahead and plug in du over 4e to the 4t in place for dt. So we're going to replace this dt up here with du over 4e to the 4t. Okay, so what we've got here is we've got the integral of 4e to the 4t over, well, realize that this denominator, 9 plus e to the 4t, is just u. So our denominator here is just going to be u. And then we're replacing the dt with du over 4e to the 4t. Okay, so here we're going to have du over 4e to the 4t. And as you can see, the nice thing about my way of doing it is as long as you're doing things correctly, usually they have them set up so that everything is going to cancel out. So here the stuff that cancels out is actually the 4's on the top and the bottom and the e to the 4t on the top and the bottom. So this one is actually a slightly different integral. Now we have the integral of 1 over u du. Now recall that the integral of 1 over u du is actually natural log of absolute value of u plus c. Okay, so this is natural log of absolute value of u plus c. And then where can we go from there? Well, there's not much else to do. All we have to do is plug back in the expression for u in terms of t. Okay, so remember we said u equals 9 plus e to the 4t, so we have to plug that in at the end here. So we have natural log of absolute value of 9 plus e to the 4t. Is that what I said? Yeah. 9 plus e to the 4t plus c. Now you might think that this is your answer, right? You would think this would be your answer. You'd think you'd be done here. But if you think about it, there's actually one little thing that we can simplify here. And what is that? Well, you might not remember this, but exponential functions like e to the x or e to the 4t, as long as they don't have a negative in front of them, these are already always positive. Okay, so this e to the 4t, because it has a positive constant in front of it, this is always, it's always positive. I mean, I guess it could get close to 0, but it never actually reaches 0 because it's exponential growth. So this is always greater than or equal to 0. Okay. So that means this entire thing, the 9 plus e to the 4t, is also always greater than or equal to 0. Right? Because 9 plus some number that's greater than or equal to 0 is certainly greater than or equal to 0. In fact, it's even greater than or equal to 9. But we don't care about that. So what we got here is because it's always greater than or equal to 0, we don't need the absolute value. It's just a little sticky detail there. Okay, so since it's always greater than or equal to 0, you don't need absolute value. You don't need your absolute value because it is already 0 or positive. And remember, what absolute value does is it makes sure stuff always stays positive. Okay, so an absolute value either has to be 0 or positive. It can't be negative, but because this is already greater than or equal to 0, we don't need the absolute value. I know it's a very finicky little detail, but it is important because I don't know if my math lab will accept it if you leave the absolute value. That's why I'm bringing it up. Okay, so we're actually going to rewrite this as ln of 9 plus e to the 4t plus c. So I just got rid of the absolute value. Okay, cool. So that's a fun one. I like that one. You probably didn't like the very end of it, but once you get used to that little detail, you just check at the end to see if your absolute value is actually needed. Okay, so now I wanted to do some examples, well, a couple examples of integrating an exponential function where the base is an e. So the integral of e to the x is the easiest one, but what do you do if your base of your exponential function is an e? So recall that e is actually a number. So it's 2.71828 or something like that. I never remember it right. You can just type it into a calculator. E 2.71828. Hey, what do you know? I did remember it. So it's approximately equal to 2.71828. And it goes on forever. And that's called the natural base. It's called the natural base. The natural base. And the reason it's called the natural base is it's the base where when you take the derivative or the integral of the exponential function e to the x, it just gives you the same function. Okay, so it's called the natural base because it naturally, when you take the derivative or the integral, it gives you the same function. It's a very cool function that way. d dx of e to the x equals e to the x. And also, the integral of e to the x dx is equal to e to the x plus c. I mean, there's other reasons why it's called the natural base, but that's one reason I like to teach. It is important. So what do you do with a base that isn't so natural? So if you have a general base that is not e, any other base, then there's a different formula for it. But the formula is very similar to the derivative formula. You just end up dividing by a natural log instead of multiplying by a natural log. Okay? So, new formula. For any number a greater than 0, the derivative of a to the x is actually equal to, we already talked about this one before, that one is actually equal to natural log of a times a to the x, or the way they write it in my math lab is a to the x times ln of a. Okay, so, well, technically this isn't a new formula, but I wanted to use this to show you where the integral formula came from. So what's the integral of a to the x dx? What's that going to be? Well, like I said, the integral is just the reverse operation of the derivative. So you can actually figure out this using the formula that we already know up here. So what you can do is you can just start on the right side. You can work to the left side. So how do we get the integral of a to the x? Well, we would actually have to divide both sides by ln of a. And so then on the left side, we would get a to the x divided by ln of a. So what that means is the integral of a to the x dx is actually going to be a to the x divided by ln of a. Because it's essentially the reverse operation. So instead of starting on the left side here and working to the right side, we're starting on the right side and we need to work to the left side. So, well, how do we get a to the x? Well, we're going to have to divide both sides by ln of a. But when you do that, that ln of a ends up under the a to the x over here. Okay, so hopefully that makes sense. Okay, and then of course, if it's an indefinite integral, you also have to write plus c. Okay, so I'll go ahead and box our new formula. But it's basically just the same formula as the derivative. It's just because the integral is the inverse operation of the derivative. Instead of multiplying by natural log of a, you end up dividing by natural log of a. Okay, and yeah, that pretty well covers it. So let's see an example using this new formula. Okay, so example. Evaluate the integral. Evaluate the integral. And I'm going to skip the easy one and go to a slightly harder one, just in the interest of saving time here. Okay, so what we got here is we're going to be doing the integral from 1 to 2. The integral from 1 to 2 of 4 to the negative theta d theta. The integral from 1 to 2 of 4 to the negative theta d theta. So here our independent variable is actually theta. That's what the integral is in terms of. So that means we're doing a definite integral here. We're going to be plugging in numbers at the end. And the numbers that we plug in are actually in terms of theta. So this is going to go from theta equals 1 to theta equals 2. Okay, but of course we have to do u substitution here because this is actually a composite function. And we're going to get to use our new formula up here. But first we're going to have to get it in the form integral of a to the u du. So up here I was saying the integral of a to the x dx. Well, x is just a variable. So I can change this and make this formula stronger. The integral of a to the u du is actually equal to a to the u over ln of a plus c. So our goal is to get it in this form so that we can use our new formula. Okay, so as usual, we want to let u be the inside of the composite function. So here the composite function is 4 to the negative theta, and the inside of the composite function is actually negative theta. So here our u is going to be negative theta. All right, so we're going to let u equal negative theta. All right, and then taking the derivative of both sides, we get du d theta equals negative 1. Okay, and then if you like to do it the way I do, I would go ahead and isolate d theta because theta is our independent variable here. So if I multiply both sides by d theta and divide both sides by negative 1, I'm going to get negative du equals d theta. Okay, and then we can go ahead and plug in negative du in for d theta up here. Okay, so what we got here is the integral of 4 to the u, because we said our negative theta here is u, and then for the d theta, we're going to plug in negative du. By the way, I have no sense of humor whatsoever when I'm teaching online. I think it's because I don't actually have people there in front of me, so I don't feel like telling jokes. But I may try to put up some jokes eventually on my YouTube page. Even though my jokes are generally terrible math jokes. Maybe I'll try to do that to, break up some of this boredom. Okay, well hopefully you're not bored though. I actually like this stuff, so it doesn't bother me. But some people want jokes and messing around and stuff. Okay, anyway, what we're going to do here is we can go ahead and factor out the minus, and then we just have negative integral of 4 to the u du. negative integral of 4 to the u du. So here we're going to use our new formula. The integral of a to the u du equals a to the u over ln of a plus c. Now, here our a is actually 4. So we're going to end up dividing by ln of 4. Right? And we still have a minus out front. So we have minus 4 to the u divided by ln of 4. Now you might be wondering, well, how come he's not writing the limits of integration? How come I'm not writing going from 1 to 2? Well, I get lazy about it. I like to just not write those limits until I'm at the very end, because I like to plug in back in terms of the original variable. And then at the end, I'm going to go ahead and plug in these numbers. But because it's in terms of u right now, not in terms of theta, that's why I'm not writing those limits of integration, because otherwise they would be wrong. Because you would have to switch them to be in terms of u, which I don't usually really like that much. So that's just how I teach. But anyway, you should have negative 4 to the u over ln of 4. And now we can go ahead and replace this u with the original expression in terms of theta. So remember, we said way back here that u equals negative theta. Okay, so we're going to plug that in. And then we have a minus out front. And remember that ln of 4 is a constant, so we can actually factor the ln of 4 out front. So we're going to have negative 1 over ln of 4 times 4 to the u, which we said was 4 to the negative theta. And this is going to be evaluated from theta equals, what do we say? Theta equals 1 to theta equals 2. So now that I'm finally back in terms of theta, I'm going to go ahead and write in the numbers again. The limits of integration. Okay? And because it's a definite integral, you want to plug in the top number first into the function, and then you subtract the function evaluated at the bottom number. Okay? So we're going to have a negative ln of 4, negative 1 over ln of 4 out front. And then plugging in, we have 4 to the negative 2 minus 4 to the negative 1. Okay? And you might not like fractions, but you do need to simplify this. So sadly, if you don't have a calculator or you don't want to use a calculator, you're going to have to rewrite these negative exponents as positive ones by turning them into fractions. So if I move this 4 to the negative 2 to the bottom and the 4 to the negative 1 to the bottom, I'm actually going to have 1 over 4 squared minus 1 over 4 to the 1. And then we still have the negative 1 over ln of 4 out front. Okay, and then what can we do from here? Well, realize that 4 squared and 4 to the 1 need to have the same denominator, so we need to build these to the same denominator. So I'm going to multiply this second fraction by 4 on the top and the bottom. Or you can just go ahead and square it out. Remember that 4 squared is actually 16. Okay, so to build them to the same denominator, I have to multiply this one by 4 on the top and the bottom. Okay, so that's going to give me 1/16 minus 4/16. And we know that 1 minus 4 is negative 3. Okay? So you should have negative 3 over 16. But then out front, we still have the negative 1 over ln of 4. Okay, and then these minuses are going to cancel out. And then the standard way to write your answer is to write the constant first and then write your logarithm second. So the way you would write your answer is you'd have 3 on the top, and then on the bottom you have 16 ln of 4. Okay, so 3 over 16 ln of 4. All right, cool. So that finishes that lecture.